gravity as a test and modification of standard quantum theory. So please, Francisco, you can start whenever you want.
Okay. Thank you, Gabriel. Thank you for Lilia and Soleil for the great course. And before I start, I just want to make a personal note, because 10 years ago, I was here, and it was when I discovered canonical quantum gravity and de Broglie-Bon theory and the whole sort of things that I'm going to talk now. And my life simply changed directions completely. And it's nice that it's a full circle that I'm back here to present. I'm coming back to quantum gravity finally using this different theory that we work on. So the first comment that I want to make is to contradict my friend, saying that he said that de Broglie-Bon is the interpretation, and that might very well be true to simple de Broglie-Bon. So I'm going to make a statement saying that the Broglie-Bon interpretation is different, a little different from what I am going to do now. That's pilot wave theory that's broader and gives different predictions. So that's why it's a different theory. So it will be clear in a bit. Okay. So that said, let's go. Let me see. So before I start, because my presentations tend to be too long for me to finish, I would like to start with the conclusions. So the key points that I want to make is that quantum gravity might induce modifications of quantum theories at low energies, because we really don't know the correct way to quantize gravity. So depending on the way, you might find low energy corrections. For example, Penrose's gravitational collapse model, that there are hundreds of models by now, but they induce those kinds of corrections. And approximate versions of Schrödinger's equation, that's the model that I will deal with it, for matter fields in curved space-time can be derived, leading to nonlinear and non-Hermitian quantum gravitational corrections to the system's Hamiltonians. These corrections could leave imprints on the CMB in standard quantum cosmology models. I'm not going to talk about standard quantum cosmology models, but that's one possible signature of those corrections. And as my friend just said, quantum cosmology makes a lot more sense in the Broglie-Bon theory. And that theory offers a dynamical explanation for the origin of quantum probabilities. That's quantum equilibrium hypothesis. That's the main topic that I've been working on for the past 10 years. So that's the main difference from my pilot wave theory from usual de Broglie-Bon interpretation. The non-Hermitian corrections that appear in the Schrödinger's equation generate violations of the Born rule. That's modifications of standard quantum theory that could generate quantum gravitational signatures in cosmology, in black hole physics, and potentially in tabletop experiments. And if there's times I'm going to talk with, because there is non-linear corrections that are much more treated and discussed in the literature, as we have seen here. And I will focus on the non-Hermitian corrections, but there are some recent developments on nonlinearities that might be useful for me in the future. I'm not going to get to that probably. So without introducing any modifications to general relativity or quantum mechanics, people have been saying that it's possible to derive effects of low energy effects in tabletop quantum systems. There is a famous proposal called the BMV proposal that supposedly if you have a superposed massive system, it has a quantum gravitational potential, and you could, by entangling two of those systems, you could find a signature for quantum gravity somehow. That in standard general relativity, it doesn't seem plausible. However, the study of this experiment naturally raises fundamental questions in quantum mechanics, because you're dealing literally with the measurement problem. You're measuring a quantum field and with a superposed state, and that leads necessarily to conceptual problems. And the literature is full of discussions on what is the correct way with dealing with quantum gravity in that regime, in these situations. Not so much in the regime, but the technical situations that we are trying to deal with. There's much discussion going on that topic. Since my research has been focused on Born rule, on pilot waves, I'm focused on trying to find on those kinds of weird situations possible violations of the Born rule generated by quantum gravitational effects. So, just a brief historical comments. Feynman's idea when he went to a gravitational conference that apparently he hated because there are a bunch of stories that he never wanted to do that again. So now how we do analyze the external according to quantum mechanics? If we have two superposed masses, how we can measure the gravitational field of this superposed mass? So he proposed that we could add a test mass like this ball here, and these two particles here would cause some kind of effect here, and we could, in principle, measure it. Of course, in 1957, that was just a crazy idea. It seems that by now, people, experimentalists, have been catching up with the idea, trying to find many different proposals. I talked about the BMV proposal because it appears in many magazines. It's very famous. It's not my particular preferred one, but it's the most, I'm going to say, promising according to other people, not according to me. But here in these references here, we have a few of proposals, like experimental setups that are possibly possible to be constructed. This tabletop experience for quantum gravity, a user's manual. I took from that paper this table here that says what? What's this table here? If you have a different quantum gravitational scheme, like if you have EFT quantum gravity, or if you have semi-classical Schrödinger-Newton quantum gravity, or if you have just classical gravity, there are people like Jonathan Oppenheim saying that gravity must be classical, or if you have a Penrose-Diose kind of gravitational collapse, or if you have this correlated World line theories, that was the last topic of my talk, if I can get to that. So there are a bunch of different signals that you can get depending on the experiments that you're doing. So single body quantum coherence experiments, something like that. You try to put your mass in a superposed state. Forget about the top part. You put your mass in a superposed state. It probably won't last. The time it lasts tells you something about the gravitational collapse mechanism that made it collapse. If nothing else makes it collapse, that's very hard to do. Another more feasible idea that has been developed in a little more detail, like theoretical predictions in this paper here, more recent, is the idea that you can build something like a superposed massive thing, but instead of calculating measuring the time it takes to decohere, you measure the effect it has on a vacuum cavity with a little mirror. You can count how many photons are here. If you have a superposed thing here, supposedly it excites photons here with the gravitational field, and it excites in a specific manner that has signatures proper to the gravitational field of this superposed mass that's different from a classical gravitational field of a point-like mass. So these experimental efforts and theoretical efforts is very interdisciplinary. There are many people, when you see the literature, it's very hard to know what you can trust because there are many people coming from quantum optics, doing all kinds of crazy stuff with quantum gravity that don't make any sense. And then there are other people coming from quantum gravity requiring that quantum optics people be much more consistent than they need to be to do their experiments because they are doing effective things. So there are many discussions in the literature. I'm literally drowning in literature at this exact moment, trying to find a consistent theoretical way of dealing with those situations in a field theoretical manner that I can treat with my pilot wave theory and make predictions on specific situations. That's where I am now. This graphic here is interesting by Aspelmeyer, is a one of the leading experimental guys in measuring gravitational fields, like classical gravitational field, is a plot that he shows where we are in our limits, low energy encounter of quantum mechanics and gravity here. If we can superpose masses of this size, we should get something different if our quantum theories are not exactly what we think they are. If they have some kind of collapse mechanism or decoherence, what's the decoherence, and so on. So that's the first part of the talk. Any questions? The experimental setups. So that's the whole motivation, because the next step will be highly speculative, and the final calculations and predictions are still being done. So I hope you get my conceptual gists more than the technical one. So gladly, we had a talk about canonical quantum cosmology right now, and Sohei already told us this is the Witt equation. If I put a matter field phi, it can be, it's probably a scalar field, but in principle we could add other things, and we get Wheeler-DeWitt equation. That's more or less complicated. Doesn't have like our friends Hamiltonian doesn't have a first derivative here. So what's time? There is another constraint equation, a momentum constraint equation here. And this is what canonical quantum gravity looks like for a field in a generic background. So that's the starting point, and as Sohei told us, that's very difficult to start with. So we try to compress the whole space of metrics to little things that we know how to deal with. So that's the mini superspace proposal that also our friend just talked about. If you have this case here with just a scalar field and the scale factor, you end up in the mini superspace model with something like that. It seems like a first derivative here, but it's not. It's very much more complicated than that. And then you get a equation that looks like that, with this minus sign here. And then, and that's the interpretational jump that my colleague, my friend, my professor, Anthony Valentini made, that if this looks like a Klein-Gordon it looks like a Klein-Gordon equation, does not have a clear way or a very consistent way to be transformed in the Schrödinger-like equation. That's what usually is done. We find canonical transformations that make this look like the Schrödinger equation. And this is fundamentally non-normalizable. And that's true even without the Klein-Gordon equation, like in this case here. But in mini superspace models, we usually, when we put it in a Schrödinger equation, we can find a Hilbert space, even though I don't think it's very much consistent, but we can do something. In this case here, we can't do much. And this is definitely non-renormalizable. So in quantum cosmology, like our friend was doing, we have to define initial conditions for our quantum perturbations. That involves defining quantum probabilities for those quantum perturbations. And although no one talks about it, those quantum probabilities obey something like a Born rule for quantum perturbations on a curved background. But as we have been saying in the mini courses, defining quantum probabilities in a curved space backgrounds is not very easy. Defining a vacuum state in one time, okay, but defining how this evolves in time, because I want this psi, this wave function, to evolve in time, and tell me how probabilities will evolve as the universe evolves. So how can we recover the Born rule if our measure for probabilities simply cannot be normalized? So that's the questions that we have in canonical quantum gravity. And there is something called the naive Schrödinger interpretation. It was not me, neither Valentini, that called it naive Schrödinger interpretation. It was Bill Unruh and Robert Waltz, because there are a bunch of problems. The most serious one is the time problem, because these wave functions usually don't depend explicitly on time. But people try to, as I said, make that equation look like a Schrödinger equation, then give it a Schrödinger-like interpretation, a Copenhagen-like interpretation. There are the most, I think I should comment on that, the most accepted program nowadays in quantum cosmology is the consistent histories approach that has been developed since the 90s. And it's a very nice approach. I would argue that histories are another name for trajectories, but that's another thing. So, what is the Ribon approach for the quantum cosmology? Gladly, he already said it. I don't need to say it again. The thing is that this pre-inflationary phase that we really don't know exactly what happens there, this opens a window for us to do quantum mechanics, quantum field theory, quantum whatever here. And if our Born rules are violated here, it's in principle possible that those violations end up in a large-scale signal in a later time. So it can give imprints in principle, it could give imprints in the formation of structure. And so dark matter formation. So since I have only 5 minutes, this is the quantum equilibrium hypothesis. The quantum equilibrium hypothesis is simple as that. The probabilities in quantum mechanics are statistical probabilities. They define a given statistical state. In thermodynamics, classical statistical mechanics, we have also that. You have non-equilibrium states that relax dynamically to equilibrium states. And all systems in the universe presumably do that. So that's the same exact logic that we apply here. We have a psi square that's a dynamical object, and we have a bunch of particles and fields and other stuff that we have to do some statistics with these things. They are guided by the wave function in the Broglie-Bohm theory. And as they don't need to be initially distributed equally to psi square. They can be distributed in any way, shape, or form. We don't know the initial conditions for the universe. That's the point. So since we don't know, they might be ones that violate the Born rule. And if they are, we must first prove that the Born rule can be achieved in the concept of parallel wave theory that has been shown extensively by numerical simulations. That's a psi squared here initially that doesn't agree with its distribution of particles in a coupled harmonic oscillator. And very rapidly, the rho becomes psi squared. But what we want to look is for violations of these kinds of stuff. So I want cases where not so much. So psi squared evolves and rho goes close, but when we put this over that, there's a small deviation. That deviation could appear here, but could appear in other places also. But what we learn from all those, my PhD work and other simulations is that it's very hard when a system starts in whatever state it starts, it goes very fast to the Born rule. So whatever we want to measure in that space-time that didn't relax, it must be a very exotic situation, maybe at very early times in the universe, or maybe if we are here in this equilibrium state, there's something that we could do to generate non-equilibrium, to get us out of this state of equilibrium due to quantum gravity, because if there is possibly quantum gravitational effects in the early universe that makes or that are responsible for non-equilibrium, if we are looking for quantum gravity in the lab, it might very well be that if we find it, we can find also non-equilibrium. So, as I don't have much time, I'm going on. That's the model that I use. It's based on this paper here by Kiefer and Singh. They do a perturbative expansion on the Wheeler-DeWitt equation. This gives us, that's a very nice feature of this expansion, because this term here, S0, obeys a Hamilton-Jacobi equation, classical, and then if we solve it as the action of GR, we have a background equation. This other equation, this other term here, S1, obeys a Schrödinger-like equation for the matter fields. So we have general relativity in quantum mechanics going out of the Wheeler-DeWitt equation. That's nice. But then we have this other guy here that gives us weird corrections. And these weird corrections here, HA is a square term, so it's the nonlinearity that I was talking about. And EHB this I here is the non-Hermitian term that could, in principle, generate non-equilibrium because, and that's how my talk is connected to the unitarity things that we are discussing in the course by Gabriel, because unitarity is essentially conservation of probabilities. If we have Born rule violations, we have violations of unitarity. So that's what kind of what I'm looking for. I'm looking for violation of unitarity in quantum gravitational systems. I also do work with Nelson Pinto Neto, so we are looking at quantum cosmological models. We are building one model different from that one, but also as complicated. And so, but as I learned about this whole field of tabletop quantum gravity, it seemed, and as I learned about this possibility here of generating quantum non-equilibrium, it seemed like an interesting possibility to calculate from that approximation here, what would be the effect of this term on systems of quantum gravitational systems like the ones that I exposed in the beginning of the lecture, like those massive superpositions or entangled massive superpositions and things like that. So just a final comment. I'm not going to go through the last slides. Born rule violations and non-linearities and born rule violation and non-unitarity are the same thing. But those kinds of things appear not only in quantum gravitational effective field theory, but in a bunch of theories, in a bunch of proposals that try to make the combination of quantum mechanics and general relativity a little more conceptually acceptable. So there are a bunch of complex terms appearing here and there. So non-linearities have been studied for a long time. What's usually done with non-Hermitian terms, that they are ignored, they are treated as unimportant. So what I'm claiming is that we should at least consider their importance, because if they can show that we can violate the Born rule, we should rethink the whole thing. Because if the Born rule can be violated, quantum mechanics is another thing. And if it can't, we can forget about the pilot wave theory being something different, because one of the only ways that it can give you experimental results different from the usual is this one. There is another, but so I will stop here, but that's it.
Questions?
Could you go back to the slide with the Hamiltonian, with the scalar field, please?
This?
Yes, this one. You see, like you said, it has a Klein-Gordon-like form, and I have seen some works that point out that when one tries to make a quantum mechanical interpretation of the usual Klein-Gordon equation, states are not normalizable because in the end, in quantum field theory, you need to have correlation and annihilation of particles. And they propose that if this would occur in quantum cosmology, you would need to make sense of weird things like creation and annihilations of universe. I would like to know, what do you think about it?
I think that you just described what I said here, that's Klein-Gordon and all weird things. I didn't say because I didn't have time, but when quantum equilibrium goes, when we have quantum non-equilibrium, all weird things happen, like signaling faster than light and a bunch of things. So yes, but that's much more advanced than we are. We have to make sense of how to do physics in this weird context where we don't have probabilities. We don't have a way of calculating probabilities in the very early universe. And the claim by Valentini is that we shouldn't, that there is no Born rule in quantum gravity, because there is no probability for quantum gravitational systems. We have one universe, so we shouldn't be doing probabilities.
Let me be more precise then. When people found out that it's hard to make sense of probability interpretations in Klein-Gordon, people attributed it to creation and annihilation of particles.
You mean like outside of our universe, it's creating things. The leakage of probabilities is another part.
Yes, maybe something like that.
So one
I
interpretation
cannot
that I have
answer
for
it.
this that doesn't need pilot wave for this kind of terms here is that we just, when you violate unitaries, may very well be that you are not counting all your degrees of freedom. You integrate to give one. When you integrate over all things that are possible. If you don't know all things that are possible, your universe is open, and there are much more things outside that we don't know, the boundary term will appear exactly like that. Because in open quantum systems, when we have a measurement, we do here. So non-Hermitian terms are very common in quantum objects and quantum measurements. That's very okay. There is an open universe proposal, but it's a many worlds proposal. But in de Broglie-Bon theory, it could be very well be that the universe, not that creating particles, but that are what we have is just an open thing that has much more things outside it.
I see, fair enough. Thanks for your lecture. I'd gladly discuss it more about it later. Thank you very much.
Thank you for the question.
We have time for one quick question now, guys. Okay, so let's thank the speaker again.